So I decided today to sort of make a case for, in particular, the value and importance of polarimetry in the both in BHEX and in sort of a longer timescale vision of space-based millimeter VLBI. And so I'll try to give you a sense of some of the reasons for that and the accretion physics in jets that we can probe using polarimetry. The work that I've been involved in that I'll talk about is done in collaboration with the people underlined here, Zach Gellis, Andrew, George, and Alex. Particular thanks to Zach and Andrew for getting me some figures at the very, very last minute. So I'll start with just a couple of very broad introductory comments, and then we'll kind of dive in from there. So in general, in accretion, we have different regimes where the gravitational energy that's liberated by accretion can either come out in the form of radiation, or it can come out in the form of outflows or the plasma going directly into the horizon. We think that most of the VLBI targets and BHEX targets are in this regime where cooling is relatively slow. And so the energy that's liberated as heat comes out primarily either in the form of outflows or through the horizon. Of course, some of it comes out in the millimeter photons, thankfully, or we wouldn't have anything to observe. Those models, prior to the development of EHT or the conception of space-based millimeter extensions, made a number of predictions of what the plasma close to the event horizon should look like. The prediction that the gravitational energy goes into thermal energy and it's not radiated away leads you automatically to very high temperatures comparable to the virial temperature. So that can approach 10 to the 11 or 10 to the 12 Kelvin with the exact amount in the radiating electrons, depending on things that we don't understand very well. Under these conditions, the plasma is collisionless. The slow cooling means that you have this geometrically thick structure like on the right, not a thin pancake like on the left. And that means the stuff flows in pretty rapidly, and so it should advect in strong magnetic fields. So the prediction is this sort of strongly magnetized, low density, very, very hot collisionless plasma in the near horizon region. And indeed, some of the basic conclusions from the EHT observations of M87 and Sagittarius Star are consistent with those predictions. The observations of the synchrotron radiation allow us to constrain the plasma properties. They're in the ballpark of what the theoretical models predicted well before the observations were made. So you can ask the question now, well, where are we going to go going forward? What kinds of observations can we make that will allow us to test in more detail the theoretical predictions for the accretion flow and jet structure in the near horizon region? And I think in reflecting on that, it's useful to understand the absolutely central role that magnetic fields play in everything about our understanding of accretion flows in jets. Magnetic fields are the fundamental mechanism that redistributes angular momentum and releases the accretion energy in other forms, radiation or outflows. And so the understanding of the magnetic field structure, its geometry, its strength, how tangled it is, how ordered it is the central theoretical problem in accretion and jet theory. And it's a huge computational challenge that we're trying to address numerically using simulations, using analytic models. But of course, it would be wise to have observations to test those models and keep us grounded in the reality that nature has produced. And that leads us to the need to measure the magnetic field properties directly, and that we can do through synchrotron polarization. So to give you some perspective of how much our kind of view of what the magnetic field structure might be like, how it's changed over the years, the early models of accretion disks were angular momentum transport and the release of energy were mediated by small-scale turbulent fluctuations in the seminal Shkron-Tsyaev model. Blanford and Payne and others at about the same time argued that large-scale magnetic fields could actually, through winds and outflows and jets, could be the dominant source of extracting energy and angular momentum. In the early 90s, the rediscovery of the MRI led again to the sort of resurgence of thinking about maybe smaller scale, weaker magnetic fields as regulating accretion flows. And then, starting about 2 decades ago, Ramesh, Igor, Sasha, and others really made the case for large-scale magnetic fields as being the dominant source of angular momentum transport and energy redistribution. As you can see, the field sort of flopping back and forth between these smaller scale picture and the larger scale picture, and that's captured today in part in this distinction between the sane models with overall more turbulent, smaller scale magnetic field structures and the MAD models with very large scale field structures. But I think it would be, one might say, mad or possibly even insane to think that we've reached the conclusion of this historical narrative of our thinking about magnetic field structures in the near horizon region. And what we really need, in addition to the development of the theory, is continued development on the observational front. The other example where I think this is highlighted nicely is our understanding of the origin of jets. There are two basic energy sources that are appealed to. One is the accretion power itself, and the other is the spin energy of the black hole. I think it's fair to say that probably the prevailing view today is that the dominant energy source powering jets, in many cases for black hole systems, is the spin energy of the black hole. There are a few reasons for that. One is the beautiful computational work, initially by Charles Gammey, John Hawley, and collaborators, and sort of one version of this is shown in this nice plot from Ramesh, which shows the jet power as a function of black hole spin, where you get much more powerful jets from spinning black holes than you do from accretion power alone, as realized in the non-spinning case shown here. But if you ask, do we empirically know which of these is the right answers? That's actually pretty tough. And the reason it's tough is it's basically the same mechanism. You have a rotating conductor threaded by a magnetic field, and you tap some of the rotational energy of that rotating conductor to power an outflow. If that rotating conductor is the black hole horizon, the energy flux depends on the area of the horizon, the spin of the black hole, the magnetic flux on the horizon. If it's the inner accretion flow, same formula, different area, different B field, but basically same idea. And the observational challenge, of course, is that the area of the horizon and the area of the inner accretion flow, where most of the accretion energy is liberated, they aren't very different. They differ by maybe a factor of 5 or 10. And so really, to distinguish between these two empirically, what we want is we want to measure the magnetic field structure in the near horizon region at higher angular resolution to understand what the field is doing on the scale of the horizon, and then also at higher dynamic range to directly connect to the jet. And so I would say that those are sort of the two grand challenges going forward. One is the push to higher angular resolution going towards the horizon. The other is higher dynamic range going towards the jet from the horizon out. You can think of these as sort of from EHT scales in towards the horizon and from EHT scales out towards the jet. There's a tremendously rich science case in all of these possibilities. Our understanding of the accretion flow structure, jet structure, ways to measure black hole spin, ways to test the Blandford-Znaic mechanism, hints, as I'll show, of the presence of a horizon. I do think it's important to stress that all of this, I think, needs to be multi-frequency. One of the reasons is that a real challenge, of course, in interpreting polarization is understanding the role of Faraday rotation in changing the polarization that you see, and also because there are achromatic features like the photon ring, like the light cylinder, that should look similar at different frequencies. And so having multiple frequencies is very important for that. So I'll try to just give you a sense of both of these science cases. and how we might be able to address some of these really important basic questions about black holes and our understanding of disks and jets. So it's been clear for at least 5 or 6 years, if not more now, that in a range of theoretical models, the near horizon polarization is sensitive to the spin of the black hole. This is true in semi-analytic models, and it's true in GRMHD simulations. And the basic reason is, so this is EVPA ticks with the background image of the total intensity and some models that George developed. And the basic reason is that the rapidly spinning black hole twists up the magnetic field more, it becomes more azimuthal. The field is more azimuthal, so the polarization is more radial. The slower spinning black hole, the field is a bit more radial, the polarization is a bit more azimuthal. This is sort of a summary of some of the computational work on this in models developed for M87 and Sag star. This is this polarization diagnostic, argBeta2, that Daniel, George, and Ben Prather developed, and that's used by the EHT. If you're not familiar with this, values of 180 are equivalent to minus 180. There's a 2 pi degeneracy, and that corresponds to more radial magnetic fields, and values of 0 correspond to more azimuthal fields. So this would be argBeta2 closer to 0. This would be closer to plus or minus 180. The GRMHD simulations, the range of values of the sort of image average polarization for Sag star and M87 are shown in the gray violin plots. And then the purple here is a very nice analytic model that George developed that actually just came out a few days ago on the archive. And then the shaded regions spanning the x-axis are the range of observations for 3 epochs of M87 and the 1 epoch of Sag star. So you see the strong black hole spin dependence in the GRMHD simulations, in the analytic model that George developed. So we have sort of, I would say, a good computational and analytic understanding of this spin dependence. The analytics sort of clarifies that one of the key properties of the plasma, in addition to the spin, is how strong the magnetic field is in the near horizon region, because that determines how the plasma inertia resists being spun up by the rotation of the black hole. So the thickness of the band shown in George's analytic models here depends on the strength of the magnetic field in the near horizon plasma. Now, there are many complications which could make this difficult to realize in nature. We might be seeing some of that in the differences already in the different epochs of M87, where there seems to be a lot of variability in the near horizon polarization. That may be variability in the field structure, maybe variability in Faraday rotation. There's the complication that, of course, the average magnetic field is not the same as the intensity weighted average. That's much more complicated, depends on where the emission is. But it is encouraging that in a range of theoretical models, there is this very strong spin dependence, and it certainly motivates improving the observational diagnostics. As we go to higher angular resolution, there's new features that become available. One of the most striking is that there actually is, under certain restrictive assumptions, specifically in the limit of time-steady axisymmetric models, there's actually a unique polarization of synchrotron radiation on the horizon of the black hole. And that is shown here in George's models by these bands of models that represent different kinematics and magnetic field strengths, all approaching the same value as you approach the horizon. Now, the horizon value is not observable, right? There's no flux reaches us from exactly that point. But remarkably, this trend towards the horizon value is observable. So Andrew has shown that, at least he wanted me to emphasize in simplified reconstructions of what BHEX plus ground would be able to do, although one cannot measure exactly the horizon value, one can measure the dramatic change in the EVPA as a function of distance from the black hole as you start to approach the horizon. And that would be really a beautiful signature of magnetic field lines threading the horizon of the black hole, and a key step towards trying to observationally test the Blandford-Znaides mechanism. So you can see that here, that the inner few reconstructed BHEX points, right, and I should say the GRMHD simulation, right, the polarization starts changing dramatically, analogous to the simplified semi-analytic model of George's shown here. Okay, so the last thing I'll say is just a few things about the other direction of, instead of going towards the horizon, looking at higher dynamic range out towards the jet. And I'll also emphasize that although this is often viewed as a ground-based VLBI project, because you want more stations to fill in the dynamic range, that the high angular resolution of space-based baselines is also really critical. I have no idea what time it is, Alex. I don't have a clock here, so please let me know if I'm
Yeah, you have
running.
a few more minutes.
Okay, good. So connecting the jet and horizon scales actually has an equally, if not more, rich science case. There are opportunities by observing the polarization extending out to the jet to measure the acceleration of the plasma as it goes out in the jet, to measure our viewing angle towards the jet axis, to measure which part of the jet is approaching us or receding from us, and to measure the black hole spin. So this is an example from an analytic model based on solving GRMHD equations along poloidal magnetic field lines that Zach Gellis and Andrew developed, showing the polarization of a face-on jet as a function of distance with the intensity in the background. And there's a very strong signature of what's called the light cylinder here, which is the radius where, as you move away from the black hole, the plasma can no longer co-rotate with the horizon of the black hole. These models are Blandford-Znaides models where the field is anchored in the horizon. The light cylinder radius is about the speed of light divided by the rotation rate of the horizon, scales like 1 over the spin parameter A. And that imprints itself on the polarization because the field becomes increasingly toroidal, the polarization becomes increasingly radial as you move outside the light cylinder. So I thought this would never be observable until this remarkable system that Yuri talked about yesterday, the Blazar 1424 plus 240, which seems to be a face-on system where you see these beautiful radial polarization ticks. This is at 15 gigahertz on much larger spatial scales than Zach's model here. But the prediction is that if we can look at higher frequencies, and this system is detected with ALMA, if we can look at higher frequencies deeper into the core, we may see the signature of the light cylinder in the polarization pattern and be able to say something interesting about the acceleration of the jet and possibly even about the spin of the black hole. The last thing I'll say is Zach has now extended the model to off-axis viewing, such as an M87 model at 17 degrees, or the exact same M87 model viewed at 45 degrees. The polarization structure is very interesting. It's actually a lot of beautiful special relativistic effects that I'm not going to go into, but it turns out that the polarization pattern that you see depends strongly on the ratio of the cosecant of the inclination angle that you're viewing the spin axis at and the Lorentz factor of the jet. And you can see that here, that in the 17-degree one, the left side and the right side has these vertical polarization ticks, the left side has the horizontal, and that basically flips at 45 degrees. And that's this flip between the fixed Lorentz factor, these are GRMHD simulations, so fixed kinematics viewed at a different angle, different polarization. And in the off-axis case, only one of the two limbs contains this light cylinder swing that I emphasized here. So that swing is still encoded in the polarization pattern, but only on one of the two limbs. And so this really highlights the importance of high angular resolution to resolve the transverse structure of the polarization. And so we really need the combination of both ground and space-based VLBI to understand the jet polarization signature and tease out all of this information that's there about spin, acceleration, viewing angle, Lorentz factor, et cetera. Okay, I'll end there, and I hope I've convinced you that just like Andy nicely argued yesterday that the photon ring is a grand challenge worthy of decades of study with interferometry, so too is the near horizon and jet polarization. There are many wonderful scientific opportunities in our study of that science, measurements of black hole spin, constraints on whether jets are powered by black hole energy extraction, better constraints on theoretical models of disk magnetic fields, the central theoretical problem in the field, et cetera, et cetera. It is, I will freely acknowledge, possible that we will be limited by foregrounds like Faraday rotation, by turbulence, et cetera. But I think that merely highlights the need for multi-frequency, very high angular resolution observations. And just like the CMB managed to peer through the fog of foregrounds, I hope that we'll be able to do so as well with black hole polarimetry. So thanks very much. Happy to answer any questions.
Thank you, Eliot. Very inspiring talk. I see Marshall already has a question.
Yeah, so I was just wondering, a very good talk, by the way. Really learned a lot there. If you had, like, say, a star that was on the process of being falling in and being tidally disrupted, or even maybe an intermediate mass black hole, would you be able to see that in the polarimetry? Wouldn't that like mess up those neat curves we just saw and cause like
Yeah, I
some
mean, I think
structure to be imposed on that?
if you literally had a star going through the system or on a scale comparable to the observations or the tidally disrupted stream of stellar debris passing through the disk or the jet, that presumably would change things in a very interesting way that I certainly have not thought through. But
I mean, that's got to happen sometimes.
that does. I mean, most of the time when stars get tidally disrupted, there isn't much of an observable disk or jet there. That's partially a selection effect, is that people are trying to find these days clean tidal disruption events where they're more confident that it's a star being disrupted and not some crazy accretion disk variability. So they pick systems that don't show much AGN activity in the decades prior when they see some bright flare in the nucleus of a galaxy. Most of those events are not producing super strong jets, although many of them do show radio emission that's probably more from non-relativistic outflows running into the surrounding gas. Alejandro?
Thank you.
Thank you. And I think it's related to the question I asked last night to George. I'm still thinking about that. I haven't read the paper, but if all these curves are just going to the same point, then in some sense, and actually it's far away from the horizon because it is even like farther than 2 for Schwarzschild, and then you go to 9 and it's still outside that. So do they don't become then uninformative to infer spin in some sense? Because they are
Well,
like farther away, but then very close to the horizon, they all are going to
yeah,
like similar point, not the same point, but similar, but then like there is this degeneracy.
just trying to find my slides, which seem to have completely disappeared. Oh, there they are. Okay. Yeah, so I didn't go into this a lot. So I think the answer to your question is that the horizon value actually does depend on spin. You can kind of see it. The curves end at different points here.
But it's tiny, right? It
I
is
didn't
very
emphasize that because I think that seems honestly extraordinarily hopeless to observe.
yeah.
So I think the spin dependence that I emphasized is the overall polarization at somewhat larger radii, and that this gradient here is sort of a signature of fields being anchored to the horizon.
Yeah. Okay.
Yes, it's a spin dependent value, but that seems
Yeah, yeah.
implausible that we will be able to access observationally on a reasonable timescale. So,
Yeah.
yep.
Thank you.
Question from
Peter?
Peter.
Hi, that was great. So I know this is included, but I just wanted to ask you to underscore it. What do you think is the single most important thing that we could do with BHEX toward a resolution of the Blanford's-Nyack mechanism? Towards, if we wanted to say which of the many things we can measure would give us the most persuasive case for Blanford's-Nyack, what would it be?
So I think there are, to quote Charles, who says this often, I think there are sort of multiple ingredients. There has to be a black hole, it has to be spinning, and there have to be magnetic field lines threading the horizon. So I think it's the combination of the measurement of the spin and the indication that there are field lines threading the horizon from the near horizon polarization. Right now, that's what I would say would be the two critical steps. You know, the ideal situation, which I think is actually somewhat surprisingly harder, would be to measure also the Poynting flux in the jet going out. And by measuring the spin and the near horizon magnetic field, you have an estimate of Blanford's-Nyack Poynting flux. The problem is measuring those two numbers precisely is actually quite challenging. So I think that step is actually also important, but challenging. So, yeah.
So would in the transverse measurement of the jet, would the polarization and intensity there be a prima facie case for Blanford's-Nyack over Blanford-Payne?
I mean, I think that honestly, no, because you would get a similar polarization structure for the magnetic field anchored in any rotating conductor. And so, you know, you could replace the argument I made here about the spin of the black hole with the rotation rate of the disk at small radii, and you could get similar models. So I think we have not seen a way to use, you know, again, putting on my very physicist hat here of sort of unambiguous distinction. I think it's hard because the mechanisms both just depend on this field lines threading a rotating conductor. So that's why the large radius measurements are, for this science case, I think important, but not quite as informative as the small radius.